Good afternoon, and thank you for joining us at today's webinar, where we will discuss the prospects of fusion energy. For those of you who don't know me, I'm Simon Barber, and I'm the UK Managing Director of Assystem. Assystem, we are the leading international engineering company working on energy transition programs worldwide. We're born in the engineering company, and we support countries across the world with their energy transitions. We take a leading role in supporting emerging technologies through our expertise in digital engineering and in low-carbon energy. We believe that innovations such as fusion energy are vital to achieve and sustain net zero. Assystem is also a leading partner in the UK's major fusion initiatives, and since 2005, we've been part of the Architect-Engineer Consortium for ITER, the world's largest fusion experiment, of which the UK remains a key partner. The reason we decided to host this webinar is that today, Assystem, together with the Institution of Mechanical Engineers, has launched an exciting new report entitled Fusion Energy, a global effort, a UK opportunity. This report looks at the vast potential of fusion to transform our energy systems. And by commissioning the IMechE to research and produce the report, Assystem wanted to help others, particularly policymakers, to understand fusion's potential and to inform them about the scale of the challenges ahead and the specific requirements that this sector needs to create the marketplace. We wanted also to profile the potential economic opportunity of commercial fusion to the UK and to communicate the potential supply chain benefits to new audiences. And with COP26 taking place in the UK next month, we felt that now is the right time to elevate fusion's potential in the discussion about how to decarbonise the world economy. The purpose of the webinar today is that we would like to discuss the report's findings, including pertinent questions such as the potential role of fusion in future energy systems, the steps that need to be taken to turn fusion reactors from scientific experiments into commercial reality, the cost drivers for fusion and the potential for cost reduction over time, the financing options for different investment stages between fusion R&D and a commercial power plant, the current capacity of the UK to support a fusion industry and the options for expanding these, and the possible barriers to fusion energy and opportunities for the UK to lead in commercial deployment. And to discuss these issues, we've brought together a panel of experts here, including several of the report's authors, who will present their viewpoints on fusion's potential for around 5 minutes each. After the presentations, we'll have an interactive Q&A session, and I believe you can ask questions via the chat function, and we will endeavour to answer as many questions as we can in the final 30 minutes of today's sessions. And so, without further ado, I would now like to introduce our key speakers today, who are, on my left, Matt Rooney, Energy Policy Maker with the IMechE and the head author of the Fusion Report. And on Matt's left, Tony Ralston, a lecturer in nuclear engineering at the University of Cambridge and an author of the Fusion Report. And then, to my right, Melanie Windridge, UK Director of the Fusion Industry Association, and James Partington, Deputy Director for Fusion, Research Infrastructures and Establishment at BEIS. I would now like to turn to Matt and hear about his work on the Fusion Report. Thank you. Thanks, Matt.
Thank you very much, Simon. Before I get into the details of the report, I'd like to welcome our audience to the Institution of Mechanical Engineers. And I would also like to thank a few people. Thank you to Assystem for sponsoring the report. It's one of the biggest and most comprehensive reports we've done in a few years, and that would not be possible without that sponsorship. I'd like to also thank my contributors, because I'm sometimes named lead author of this report, but that's a little unfair to my co-authors because they did most of the research. So that's Tony Ralston from the University of Cambridge, and now who have moved on to international opportunities, Professor Giorgio Locatelli at the Polytechnic University of Milan, and Professor Ben Lindley from the University of Wisconsin-Madison. I should say none of us are presenting slides today, but you can download the report online if you haven't done so already. It's imeche.org, and in the top right is Policy and Press. You can download the full report and the summary for policymakers. So it's been interesting writing this report because it's such an exciting time in the fusion industry. There's so many things going on that we've had to edit the report as we've went along because there's so many announcements. Thanks to you to Bays, by the way, for making life difficult for us. Then this has included government funding a year or so ago, government funding for tokamak and for STEP. Tokamak Energy and First Light Fusion have announced major expansion plans. General Fusion announced that they're going to build an engineering demonstrator at the Culham site. We had the Regulatory Horizons Council in how to make commercial fusion a reality in terms of regulating it in a commercial environment. And of course, just this week, we had the UK's fusion strategy published, which is very interesting. And that's just in the UK, by the way. So internationally, over the last 10 years, there have been around 15 startups created. So fusion is no longer the preserve of national laboratories. There are many exciting startup companies that are starting all over the world, particularly North America and in the UK. There's been the New York Times reported, there's been over 2 billion of private equity funding has gone into private fusion companies, which is pretty impressive. I'm told that's more than fission, but I don't have a stat to back that up. And in terms of patents, there was an interesting study published, I can't remember the journal paper, but it was using Fusion Industry Association members and to see how many patents they've filed over the last 10 or 15 years, and it has increased more than tenfold in the last 10 years. So there's a lot of IP being submitted. So Simon covered what's included in the report. It's quite a big report. The full one is 22,000 words, so I'll let you all digest it in your own time, and please feel free to get in touch afterwards. So what I'm going to cover is the role for fusion, the steps that can be taken to commercialize fusion power plants, a little bit on the cost drivers of fusion, but Tony is going to cover that in more detail, and then a bit about the possible barriers to fusion and the potential opportunities for the UK. So why do we need fusion? Well, fusion isn't going to happen tomorrow. So it's going to, if it comes along, it'll be commercialized, we think, in the 2040s and 2050s. So we're looking at the electricity and energy market in the 2040s and 2050s. Some companies might think they can commercialize in the next 10 years, but I think even if they commercialize the first plant in the next 10 years, it'll still take another decade before you take a big chunk out of the global energy market. So we looked into the energy market in the 2040s and 2050s, and the projections still say there's going to be a huge demand for low-carbon electricity. So solar and wind will most likely dominate electricity systems, but because of the intermittency of solar and wind, you will need low-carbon dispatchable electricity as well. And so nuclear fusion, we think, will compete in a market with fission, with maybe fossil fuel carbon capture and storage, large-scale energy storage, or biomass. And fusion has advantages over all of those technologies in terms of sustainability, which I won't go into detail right now. So in terms of the challenges in fusion, there are obviously technical challenges in commercializing fusion, no matter which particular technology you choose. A lot of these are based around materials that can withstand the demanding conditions inside a fusion reactor. There's lots of detail about that in the report. I'm not a fusion engineer, so I won't try to go into detail about it right now. Maybe Tony will touch on it a little bit, because the engineering challenges inform the cost challenge as well. So the next challenge for fusion will be the costs. And there are some interesting decisions to be made in the rollout of fusion in terms of when you stop the R&D and you think you've got a good enough fusion reactor to commercialize, and then you start trying to get cost reduction through production learning and economies of volume and other things like co-siting and co-generation and things like that. In the report, we've laid out what commercialization might look like. I read a book edited by my old supervisor, Bill Nuttall, which Melanie contributed to as well, Commercializing Fusion, which had some various ways you could commercialize fusion, but we have looked at it in a basic jet ITER demo program, where you have a 4-step program to commercialization, where you from ITER, which is the experiment that proves the technology. You would have demo or STEP, which is the engineering demonstrator, which will produce electricity but will not necessarily be a full commercial power plant. You'd have phase 3, would be a first-of-a-kind power plant. If you think of the early offshore wind programs, or even Hinkley Point C, it's not a first-of-a-kind worldwide, but it's a first-of-a-kind in the UK. Whenever you build something the first time, it has inherent extra costs because you haven't built the supply chain and the skills, or the project management ability yet. And then there's phase 4, which is commercial deployment, where it has to compete on a level playing field against other similar technologies. So other smaller challenges, I think regulatory challenge, I think it used to be called a challenge, but the BEIS have published a document, I think, that has confirmed that the regulatory environment is going to stay the same and evolve from what it is right now. From the IMechE, we talk about skills a lot. We're very excited about fusion in terms of high-skilled jobs, and a project like STEP could produce lots of high-skilled jobs, and the only thing we would say is young people will be very excited to work in fusion because it's one of the big clean energy programs of the future, but they also need to have a messaging campaign to show that they have a long-term career in the industry. And finally, on to the opportunities for the UK and the broader and worldwide. I would say there's a couple in the medium term in building an engineering demonstrator. One thing is it's not going to be built in the southeast of England. I used to work for the Science and Technology Facilities Council, and it's not going to be built in Oxford. People in the north always used to complain when the big facilities were built around Oxford. So they have selected the 5 sites that STEP could be built on, and they're all in the regions where you could deliver high-skilled, well-paid jobs. Then the extra benefit for the UK in terms of developing fusion, of building an engineering demonstrator, is building up the technological capabilities and the supply chains, because the supply chains in every country across the world for fusion are immature, because all of the fusion facilities right now are experimental. So by building a demonstrator, you could build up the technological capabilities, the supply chains, but most importantly, the project management skills, which in big, complex subjects like this is very important. And Giorgio Locatelli, one of our co-authors, is a world expert in that sort of thing. Then in the longer term, there might be export opportunities if the UK decides to become a leader in commercial fusion. Fusion power stations would have lots of components that are manufacturable, therefore suitable for export. And also, fusion would not have the same regulatory hurdles to export as fission as well, so the market might be a bit smoother. And finally, I would say, if you look at complex industries, sometimes they evolve into a market where 1 or 2 companies, big companies, dominate the market. If you think of aerospace, you've got Boeing and Airbus having 80 or 90% of the market. And if there's going to be a Boeing and Airbus of the future in fusion, I think the UK should want to keep its toe in the water. Thank you very much.
Great, thanks, Matt. And could I now hand over to Tony, please?
One way of looking at what we've been doing is about the industrialization of fusion. How to turn fusion from large and novel physics experiments into something that's useful and produces economic power. As Matt mentioned, the mainline development strategy being followed goes through JET in the UK, which is an EU project, and related machines around the world, Alcator and NSTX in the States, K-Star and East in China, all of the same basic design, tokamaks, and they've been all breaking records in fusion. But they're all too small to be self-sustaining. And therefore, the second phase is the project Inita, which is getting a lot of attention now, being built in France, but as an international project with partners in all the main countries. It seeks to start operating in 2027 and its aims are produce about 500 megawatts of energy, power, in the reactor for about a length of 100 seconds and have a power gain of 10 times. That is 10 times the amount of power you put in, you get out. This is aimed to be achieved in 2035 with the first active plasma experiments where they put deuterium and tritium together in, and this is the real test. So the real test of ITER is in 2035. The third phase is demo, which seems to be called STEP in the UK. Demo is a concept which is widely just the next project after that. A follow-on power plant in the 2040s that uses the physics and magnet technology and materials that ITER has proven and adds on the systems for a power plant. That is making tritium, turning the fusion energy into sensible heat, This is mostly neutrons in the case of fusion, so you have to slow the neutrons down to turn them into sensible heat, and then turning that heat into electricity. So this is the main line of early fusion. There are many other ideas which we may touch on, but they seem, at least to the fusion community, which we've had to take into account, to be further from fruition and need more work and more science to become sources of electricity. So we're assuming in this report that ITER is successful, it proves the physics, and therefore we're focusing on demo, and which is the precursor to fusion plants, can be built and replicated. Now, to examine this, we have to look what's in the industry. In the industry, there are two whole system codes which look at the fusion, they look at all the whole systems, and they look at the energy as well. There's a code called ARES in the US, which is widely used, and in Europe, there's an equivalent code called PROCESS, which most of the work comes out of Column and is a standard work. So we've reviewed and built on the published studies which come out from these codes and tried to answer the questions: what are the practicalities of turning physics experiments into power plants, and what are the economics of such devices? But a caveat first. We have to recognize that fusion economics is quite uncertain. It's yet to be demonstrated as a principle, and all the current devices are experimental and are state-of-the-art, so their costs are very extreme. And also, there are very few economic studies being available. I think they're all referenced in the report. A handful of economic studies in the last 20 years. Nevertheless, we can look at the main issues of competitiveness. And by competitiveness, we mean competing against energy systems, zero-carbon energy systems in 2040 and beyond. And these are largely renewable. And their system costs, that's the costs of the basic energy plus the things in the system to make them to a reliable power plant, are in the range of 60 plus pounds per megawatt hour. So that's the target, if you like, for any new zero carbon entry like fusion. So the results, which you can find in figures 5 and 6 in the report, what we find is the capital costs of demo-like devices are high, which is a problem, and they're dominated by magnet and vessel costs. About 50% of the total power plant costs are in magnets and in vessels. And we end up with £8,000 per kilowatt electrical for the first of these proper plants, more than Hinkley in terms of specific cost, but reducing to about £6,000 for the 10th unit, a more mature unit, but it's still very expensive. When we look at the energy cost that comes out of these things, they're also high. So again, from the first off plant, we're talking about £150 a megawatt hour. And this then reduces as you go for a more mature plant. Now, the question is, why are these costs high, and what can we do about it? Well, they're high for two simple reasons. One is the power availability of these early machines is low. And that's for two reasons. First of all, they're pulsed mode of operation, where they operate for about 3 minutes, have a pulse of power, and then for a minute they clean the plasma out and then reignite it and have another 3 minutes. And they go through these things. It means you're losing 1 minute in 4. And the second reason is that because of the damage to the vessels and the blankets, you have to shut the plant down every few years to replace these components. And as a result of that, the utilization, the power availability of these plants is low, about 55%, whereas big power plants like Hinkley work on the basis of 85 to 90%. The second one is the overall power efficiency is low. First of all, the low temperature power cycle adopted for material reasons, and the high energy requirements to drive the plasma and to run the magnets and cooling systems means the net power efficiency is down at 25%, quite low. Well, there are solutions. What are they? First of all, there's things in the way you do the project, larger reactors, demo designs, some of the demo designs are as big as 1.5 gigawatt, making use of the economies of scale, lower costs as the things get larger. Other ideas are increasing volumes produced of the same standard design, production engineering, very similar to the ideas being promoted in this space of small modular fission reactors, and lower financing costs from shorter and more dependable build schedules, because most of this kit will be built in factories and not subject to the uncertainties of site-built stuff. Beyond that, there are more advanced designs being considered, with technology becoming available perhaps 10 years after the first demo that could address steady-state operation, removing that lost time, better materials that allow longer periods between maintenance, and higher power efficiency because of higher temperatures. And the effects of these can be seen again in the charts. As we said, estimates are rather uncertain, but as far as we can see for now, only the advanced technology and repeated production of these large units will get the cost to be competitive at about £4,000 a kilowatt electrical, which at 7% discount is power prices of about £70 a megawatt hour. I think this is in the regions of being competitive. So that's the mainstream large tokamak approach, but there are alternative fusion strategies being proposed, many of these based on tokamaks. These aim, first of all, to cut the very long timescales of development of jet ITER, bringing forward the fusion plants to 2030s, and generally they're privately funded. So the ideas here are private funding and innovation to bring things forward. And as we mentioned some of them, General Fusion, who are coming to the UK from the States, Tokamak Energy, which is homegrown, TAE Systems in the States, Commonwealth Fusion linked with MIT, and First Light, who are, again, a spin out of Oxford. They aim to cut the capital costs by being more compact and making fusion more affordable. Many of these, not all, but many of these things, the key technology is high temperature superconductors. And by high temperature, I mean they're operating at perhaps 10 or 20 Kelvin. They're not particularly high temperature, but they're high temperature superconductors. And the main thing they do is because they can take higher currents, they can get better fields, achieve higher magnetic pressures, and therefore this drives a smaller size. A lot of people are producing spherical designs, the shape of an apple rather than a sort of ring, to radically cut the device size and hence capital costs. And this is a feature of ARC from MIT, and also it seems, although the design of STEP is not very clear from column. And then the more compact designs, very small designs, Tokamak Energy with their ST50 are looking at a very small device. The 150 is 1.5 meters radius rather than 8 or 10 meters. This is a small device, but still produces a lot of power. Faster to build, better able to take advantage of the economies of power. A little caveat about these smaller devices. It seems these designs will need, as well as the high temperature superconducting magnets, the same advanced materials and blankets as advanced large to be competitive. And these technologies may not be available until before 2050. So it's an exciting time. There's lots of technical challenges which translate into economic challenges ahead.
Great, thank you, Tony. And now if I could hand over to Melanie. Thank you.
Thank you very much, Simon. It's a pleasure to be here today. So when I was doing my PhD in fusion energy about 15 years ago, I remember beginning to feel a bit demoralized because of the seeming lack of progress. It was around 2006, and the ITER partners had deliberated for some time over where the machine should be sited before deciding on Cadarache in France. Site preparation began in 2008, and the foundations began to be laid in 2010. I had come into the field full of youthful excitement for the potential of fusion energy. I was told that fusion was 30 years away. As my PhD neared its end, I realized that fusion wasn't now 27 years away. If anything, it was predicted to be longer. But then things started changing. Now, the situation feels completely different. After years of site construction, the ITER tokamak is being put together. We can see videos of huge magnetic coils being delivered and other giant pieces of this complex machine coming in from all over the world. Even more exciting to me is that numerous private fusion companies are now on the scene. They're pushing harder to more ambitious timescales. They're making use of new technologies and developments, particularly materials, as you've heard, such as high-temperature superconductors, which make higher magnetic fields than previous superconductors, meaning that fusion devices could be made smaller and therefore cheaper. These high-temperature superconductors only began to become available commercially just over 10 years ago. Another important advance is that of high-performance computing, which allows researchers to make better simulations and models and to optimize operating scenarios and to improve design. To date, we've seen almost $2 billion of investment go into private fusion companies, and that's only set to increase. And what has been starting to happen over the last few years is that public-private partnerships are being set up so that private companies can work with public fusion laboratories to make use of the extensive experience and facilities at these labs. This is a huge step forward in tackling the wider challenges required to move fusion out of the laboratory and towards a commercial energy source. Now that the world is taking more notice of climate change and governments have net zero targets, we're also seeing more signs of government interest and support. The United Kingdom has recently published its fusion strategy, outlining its plan to commercialize fusion energy, and it's also pioneering a regulatory framework that's appropriate to the technology. In contrast to those PhD years, I feel that momentum is truly gathering. The Fusion Industry Association represents the growing private fusion industry. We now have around 25 private companies all working to commercialize fusion energy soon enough to contribute to climate targets. We welcome the UK government's fusion strategy and green paper on regulation and the growing interest and support of fusion. Additionally, this new report is an important look at fusion energy going forward in the UK. It's a look at how we could take the technology from laboratory to commercial power plant, a process that's already beginning to start in the private companies. It's a look at how investment might support this transition. It's a look at the barriers and opportunities to commercial fusion deployment. As we go forward, I hope to see more cost studies of private fusion concepts to add to the literature alongside the ITER route to fusion. This report's analysis of key cost drivers and means of cost reduction will be instructive for those designing and developing fusion power plants. This report states that fusion, because of its potentially unlimited sources of fuel, could perform a crucial role in widening access to low-carbon electricity and hence form a key part of the post-2040 electricity generation mix. I'm convinced that fusion energy needs to be part of our low-carbon future. Recent breakthroughs in fusion around the world, coupled with decisive government support in the UK, give me hope that we will get there. Thank you.
Thank you, Melanie. And lastly, over to you, James, please.
Thank you, Simon. Thank you very much for having me. I think you gave my full job title, but for those of you who just want to remember what I do, I'm the Senior Civil Servant with responsibility for fusion policy. And thank you very much for having us today. It's a bit of a shame we're not here in person, but I hope because we're on a webinar, we can attract more people and get a few more people listening to us. Thank you very much for running through the summaries that you've given. Matt, I think you did a really good job of setting out some of the documents and the reports and things that have come through, and Melanie, like the excitement that I think we all feel with, I guess, some political interest and a bit of money behind fusion. You both gave the quote that I was going to use, which was about $2 billion being invested in private fusion opportunities. I mean, that's hugely exciting from where we sit, and it's the kind of thing that we're looking to crowd in from a UK perspective. And I think this report does a really good a really good job of putting the spotlight on fusion and the opportunity that there is, and the challenges. Tony, as you set out, I think there's some significant challenges, but I think this is an area where UK government has got a healthy risk appetite, and it's something that the upside is absolutely huge. I don't think I need to tell anyone here why we're interested in fusion and why we're looking at this. But absolutely, it's the public sector and the private sector working together. You talked about those opportunities that you're starting to see in terms of public-private partnerships. And from our perspective, we think about how we're turning this from an R&D policy into almost an energy sector, a nascent energy sector. And I come on to talk about some of our work on fusion regulation. Yesterday we had the Global Investment Summit. I know fusion companies were present there. I haven't actually found out how that went and how that felt, but I'm sure there's a buzz around fusion because there always seems to be a buzz around fusion. It's a very exciting opportunity. Just have to look at the money that's been invested to date. From our perspective, we think about what can we do, creating regulatory certainty, creating a strategy, a policy position that government stands behind, long-term policy. Very pleased to be able to stand here and show you our Towards Fusion Energy, both titled The Fusion Strategy and our Fusion Green Paper. It does feel a little bit like strategy overload sometimes coming out of government. I'm sure many of you sit there and think that. But I don't think I can sit here without talking about the net zero strategy that was published yesterday. Clearly, fusion is not part of our plan to get to net zero. It is mentioned in there. It's mentioned in there appropriately. This is very much a plan to stay at and help other countries get to and maintain net zero 2050 and beyond. So you talked about the opportunities. I mean, there's a really big export opportunity here. The UK is very lucky to have so much offshore wind available to it, but many other countries around the world will not be able to do that. In terms of our strategy, I've mentioned it here. Just the two things I thought I should point to, the two very clear goals: developing the commercial viability of a fusion prototype reactor in terms of STEP. And we mentioned the 5 sites that have been shortlisted in the news recently. I should just say, STEP is not there to compete with the private sector, but to stimulate the private sector. We very much see it as doing that. And the second part is building a world-leading fusion industry, and then we can use that to export fusion capability and technology around the world. You see some of that in terms of the investment through General Fusion at Culham and what we're doing there. You're right that Culham is in the southeast, and STEP, the sites you see where they've been shortlisted. Please do read the Fusion Strategy if you haven't done so. It is quite light and it's a good read. I say so. I think it's quite an accessible read from a government document in something that's a highly technical area. The other thing I wanted to mention was the Fusion Regulation Green Paper. I can't remember who mentioned it, but you put it very, very well, probably better than I will. But in terms of regulation being appropriate and proportional, to maintain confidence from the public in nuclear technology, that it has human and environmental protections that are appropriate. And there's public assurance in the technology, and what does it mean for them? Because I'm not sure everyone in the public knows as much about fusion as the people here and on the webinar call today, but also to give business the confidence to invest. So at headline level, what are we doing in terms of a fusion regulation? Matt, I think you mentioned about what we're doing. This is our proposal. If you like the sound of our proposal, can you please feed that back into us and not just think that sounds good, but come back to us and let us know. But that's to maintain the existing broad non-nuclear regulatory approach. When I say that, that's the Environment Agency and HSE in England at the moment. And we say that because whilst fusion will have, I guess, radiological hazards, a power plant will have those at an increased scale from what we see at the current reactors. They're not thought to be fundamentally different from current fusion research facilities. So we feel this is an appropriate recommendation. The other thing that we'll be doing is clarifying fusion's status with regards to existing nuclear regulations. So that's something that we'll be looking to do. And then you talk about the timeframes. We're going to make sure that this is kept up to date periodically, and we'll continue to consult and work with the industry so our fusion regulations are appropriate and continue to be fit for purpose. So I mentioned about keeping in touch. Please do go to gov.uk and you can search Towards Fusion Energy. That's our regulation. A bit like Christmas shopping, both need to be done by Christmas Eve, so just to bear that in mind. If you want to talk about policy, my team are very happy to talk to many people. I'm sure many of you know them already, Adam Baker and Edward Lewis-Smith. Certainly talk to many of you. We have an email address which is called fusionregulation@beis.gov.uk. That's beis.gov.uk, fusionregulation@beis.gov.uk. And then I know there's a huge amount of commercial work as well that's happening. So I think Tim Bestwick's on the webinar, but many of you might know him from UKAA. And I think they've got an event lined up in early December to talk about commercial opportunities within the fusion sector. I might stop there. Thank you.
Great. Thank you, James, and thank you to all the speakers today. That's been really helpful and enlightening. We are getting some questions coming through on the live chat, which is great. You perhaps won't be surprised to know that a number of them were on the topic of safety and regulation. So I won't necessarily start there because I think that was a useful summary, James, and I think probably helped to cover off a number of the questions here. But perhaps a slightly different angle, which I think builds on your response, and Melanie, I'll probably look to you to come in on this one. And that's around the social acceptance of any new technology. So, from your perspective in the Fusion Industry Association, what would you like to see being done to generate the enthusiasm, I guess the knowledge and awareness of fusion, and how you build that support for fusion in the UK with the general public?
Thanks. I think that's a really interesting question, actually, because at the moment, I feel that, I think you mentioned that not that many people really know about fusion. I mean, in this community, I'm sure the people on the webinar do, but I think much wider than that. It's still a relatively unknown technology. And so I think gradually that has to change. It starts with education. It starts with just informing people, right from, I mean, they do learn about fusion a little bit at schools, but it starts informing people about what fusion is and why we need it and how it's coming. And then I think there will be, and then it extends to, as you get further down the track, actual dialogues with communities, like where STEP is going to be cited, for example, and making sure that the communities understand about this technology and what its impacts are for them, and what it means. So I think that as we start seeing more happening around fusion, as it's mentioned more in government strategies, in the news and things like that, people are going to start hearing about it more and thinking, oh, what is this new technology? And then we'll have to be ready to engage with them and to help them to understand more about what it is and importantly what it means, both on the benefit side and on the risk side. But I think that the regulation and the framework that we put around that, it's also very important because, and that's why being appropriate is really important, because you want to have something that's going to protect the public, but that's also going to stimulate innovation in the sector and not be overkill, you can say. So I think that that's why getting the regulatory framework right is a really important part of the picture, so that it can give the public confidence as we start having these discussions down the track.
Absolutely, thank you. And James, do you see a role for government in enabling this type of generation of public acceptance?
I think so, and things like publishing a strategy to tell you what our plans are, publishing a green paper on regulation, I think are two very good first steps. I think as soon as you engage people in like the idea of fusion, of near unlimited green energy, I think it's something you can get very excited about. And I think that whenever I go and talk to anyone, or I have anyone who's been to visit a fusion facility, they come away hugely energized and enthused about the opportunity. And so there is clearly a role for government, but I mean, government can't do this alone. Industry has got a huge amount of expertise, and I think this is something where we can work together to talk about what the UK is doing for fusion, for the UK population, but for also business. I see it as a joint conversation.
A brief question from me, if I may. The announcement this week on the 5 sites, I think 4 in the north of England, 1 in Scotland, as potential host sites for a STEP demonstrator in the UK. For me personally, that's really exciting. What's kind of the next steps within that process?
So that's the shortlist. There's going to be ongoing work by the UK Atomic Energy Authority to further drill down into those proposals to look at like the relative strengths, the relative benefits, some of the challenges, and to produce a preferred bid. I was going to say next year. I mean, that's a bit loose in terms of definition, but I mean, I can come back to you with the specifics. But it's to continue to drive towards a site. I mean, those sites, as you've mentioned, are not near where there are existing fusion facilities, and then there's a whole conversation about building a public understanding, looking at the skills base, and looking at the whole wider long-term plan that you need to continue to progress STEP as it moves from a concept and in terms of phase 1 into later phases as we start to design it and and I guess really get boots on the ground.
Okay, thank you. There's a question that's come through which I think is a really important consideration, and I'll probably turn to my left first of all. The net zero report that was issued yesterday clearly presents some really good news for SMR. And in terms of the government's plans around Build Back Better, we're seeing investments right across infrastructure in major programs. And as our system, as our partners and competitors and clients in the industry are seeing, there's a real pinch on resources in the UK at the moment. And just in the area of fusion and fission, fusion, SMRs, we'd like to see these as part of our energy future, clearly. So what's your view on skills and the skills that are available in the UK to actually deliver and realise a fusion programme? I guess from my point of view, it would be useful to touch on the context of the UK, which leads the world today in terms of fusion through JET and MAST-U. Is there a risk to the UK's ambitions by ITER coming online? And how do we maintain our position as a global centre of excellence for fusion?
Well, I think by building new facilities, you create the demand. Because I have friends, many friends, members of the Institution of Mechanical Engineers working at ITER. When ITER construction finishes, they might want to come home. But I said in my opening statement that kids are very excited by things like fusion, and they really want to take on the big challenges like clean energy, decarbonisation, sustainable energy. So they will be excited about it. They just need to know that the jobs are there. You are correct in that we produce reports every year at the IMechE and all our PIs about a lack of engineering skills and technical skills. So we'll really need intervention by government, continuous intervention by government in terms of funding for new training skills, working with academia and so on to promote engineering. We bang on about this year after year after year, and we will continue to do so. But I think fusion is one of those industries that people will be attracted to if they see it as a viable career option. Tony's from the University of Cambridge.
Yes.
Well,
I would say that that's a slightly different way. I think that the issue about skills is one that's worth considering. If you go to Culham today, there's the big jet building, but then there's quite a big program existing for the Atomic Energy Authority. And then on the same site, Tokamak Energy have got lots of private funding and are going to build a device and are working away on that, and they're doing prototype experiments. There's the mast upgrade there, and there's the STEP program. So you can always tell when a place is full because you can never get a car parking space, and that's true every day. And then we've got General Fusion going to come with $300 million or something to build a device on the same site. So this site is quite important in Europe. ITER is happening in France, and it's a huge site, but actually Culham is a very big site, even though JET will run out in a short while, and is a magnet for people. And I guess if we build STEP somewhere else, this will also be a magnet for people. I think the timescales of these things allow people to be attracted and to move on to it. I don't think you should be at all negative about these opportunities. We got worked up in the fission business 10 years ago about the nuclear renaissance and whether there'd be enough people to go around. Well, nuclear renaissance was delayed, and there's always been enough people to go around. And if not, universities like Cambridge or Oxford or anywhere else can generate courses. We started a course 10 years ago aimed at the nuclear renaissance, and we've had 150 very top graduates through our program, and we could do more if required. So I don't think the training is a problem. I think the key area, if we're talking about competition and maintaining our position with French, is what is our core competence? What is it that we're good at? And that's what we should be focusing on. And I think one of the things we've learned doing this report and talking to the people in the AEA is they are very much of the view that having JET here and having the design work here, that this systems analysis, overall looking at the systems, is the the key advantage, the competitive advantage the UK has got in this, and puts us in a good position to design things like STEP and other devices. And I think as long as we are not letting that wither and we're building on that, I think we will maintain our position, even if the focus of the experiments will bound to move to ITER, because that's where the action will be from 2027 onwards, and that's where we're going to get the data from. We need to pull the data out and use it. And I think the announcement by the government to commit to STEP is very timely and very useful, because it enables us to say there is going to be a UK programme to work with and to feed off ITER. Otherwise, I think you might find that our position would get weakened.
Thank you, Tim. Melanie, is there anything you'd like to add?
Thank you. Yeah, I don't have much to add on the skills development, particularly to what Matt and Tony have already said. But one thing I do think is really interesting about fusion that comes into it as well, from when children are learning about fusion and getting excited about fusion at school, is that fusion, it's not just engineering or physics. Like, there are actually lots of different elements that come together to build a fusion power plant. And so people can get involved in chemical engineering, materials science, cryogenics, neutronics. You know, there are various different roles and people coming together with different skills. And then even outside of I know we're talking about the skills and the construction and the building, but even outside of that, there are people who work in policy and people who work in communications, and there are so many different skills that are going to be required to come together to build the fusion industry and to drive fusion forward. And so I find that really inspiring as well for children coming up into it. You can be involved in a really interesting field, even if you're not necessarily a physicist or an engineer. There are different ways of approaching the problem.
Absolutely, and I think in the move to modular plants, for example, there's a lot of similarities with other industries and a lot of cross-industry and sector learning, I think, that comes into this development life cycle, which I think comes to help as well. Coming back to a couple of questions on the chat. So I'm going to have an attempt at combining these. So there's a question here about you talked earlier about fusion's always 3 decades away, and so there's a question here about how do we accelerate that development time frame with fusion, and I think aligned to that. One of our younger audience members has asked about the role of simulation within fusion. So I think there's some questions here about the role of high-performance computing and AI and digital simulation within the development of fusion systems, and how that could potentially enable us to get to a commercial viable solution quicker.
That's right. I think definitely one of the drivers behind these private equity and these projects that have been grown up is people's frustration in the industry of how long it takes. Instead of it being, you have different phases of physics and demonstration and such. If these each take 20 years, no one's going to live long enough to see the outcome. And what they want to do is cut this to same cycles you've got to go through, but perhaps 5 years. By doing things at a smaller scale, you reduce the amount of money, reduce the complexity and such like. And if you can make these things work, these are the real advantage. It's interesting having listened to the debates in the fusion community. They've said the idea of small reactors have been around for a while, but they poo-pooed them. But actually the big guns have had to come on board because they realize the drive to do things on a faster timescale, and that they may be possible. I think the ARC system, which has been designed by MIT, is quite a good example. It started off as a group of PhD students in 2015 who published a report on ARC and the precursor Spark, small reactor timescales, looking at the technology. And these PhD students, using the modeling tools that they had there, and the experiments that came out of the Alcator-C machine that they have at MIT, they came up with a feasible project, and this has now been funded privately by Commonwealth Fusion in 2015. So a PhD student finishing in 2015, they are building Spark right now, and they intend to follow that 5 years after it with ARC. And so this timescale is completely different from the approved international one, and if they're successful, they'll get ARC running before ITER. It has risks associated with it. It has made use of the tools. It's made use of the enthusiasm of some PhD students working together rather than just following the lines that their greybeards have said, oh, this won't work. And so it's very exciting. And of course, private money has enabled them to do that. They didn't have to go through all the committees and reviews. It was not rigorous to get this money, but the private equity people saw the opportunity and are willing to fund these people, and they're funding them hundreds of millions of dollars. So I think two things: modeling and the enthusiasm of youth, and smaller things with shorter bounds will get us there more quickly, perhaps.
So just to add briefly on that, similar to Melanie, I worked for the Science and Technology Facilities Council from 2005 to 2011. I used to work in particle physics, but there was lots of other stuff going on in space science and fusion research. At the time, I was very pessimistic about fusion as well. ITER was already over budget and behind schedule, I think. We had an exciting proposal for a project called HYPER, which was laser-driven fusion, which never got off the ground. And then fusion seemed to go away for a few years, but the thing that sort of changed my mind is if private sector funding, if that much private sector funding is going in, that tells you something. And I think on the research, I think having many parallel streams of research is a good idea. It's in innovation, we call it fail fast. People maybe don't like using that term, but if you fail fast, you can learn and move on. The one thing that I think will be possibly most different is the materials testing facilities, because the private sector firm can't have a nuclear reactor bombarding neutrons at a piece of metal for 10 years to find out what happens. So that will be a key public sector thing to do. And if we can accelerate that, that will accelerate the whole fusion program.
Can I add something, please? To add to that, on the subject of timescales to fusion, I think it's always the hardest question to answer, and it's always the one that gets asked because everybody wants to know, right? When are we going to have fusion? I always say it's science, it's an exploration. Like we don't know exactly what we're going to find, and that's why it's so hard to make predictions of the timing. But we have plans, we have targets, and those are the things we're going to work towards. And I agree, the private companies coming into the space are exciting because they are trying to do things faster, and Tony gave a really good examples of what's being done, and try and make them smaller, and then you can iterate faster. But we still need more than that. We still need more funding for starters. Yes, $2 billion going into the space is a lot, and it's impressive, and it's great. But that's spread amongst various private companies. I think the top four best funded companies have probably about 80% of the funding. But then there are others. As I said, there's around 25 private companies that are members of the Fusion Industry Association. So it's spread out. And ultimately, even if you're trying to make a small fusion reactor, it's going to be big, right? It's not going to be like in your car sized. It's still going to be relatively expensive. And so the barriers that the private companies are going to come up against is they're going to get to a point where they've iterated on the small scale, they've proved that their concept works so far, and now they need more investment to get it to a stage where they can actually demonstrate, let's say, energy break-even or first electricity. And these plants, even if they're smaller than ITER, they're still going to have hundreds of million price tags, maybe even $1 billion at a push. So they're still going to be expensive machines, and so that's where government needs to help to leverage private investment and to create the climate that's necessary, so that we can see that level of investment that's necessary. So that's one big thing, and the other big thing, which I mentioned before, is the partnerships. We really need public-private partnerships. It's not private sector against the public sector who's going to win. The media love to portray it like that, but it's not realistic because there's so much that needs doing around as part of this journey to commercialization, which cannot just be done by one single company. And Matt gave an example of some of those things, like the materials and the testing that's required. So we need to start doing more things in parallel if we want to get there faster. Instead of waiting for ITER or whichever fusion device proves we can get past break even, and then tackling the materials testing, and then tackling the tritium breeding, and then, we need to start looking at these things. And that's why actually Cullum, it's really interesting at the moment. They're building other facilities on that same site so that they can look at some of these very things. And these are the challenges that are going to take us to commercialization. So that's how we're going to get there faster, by having the right kind of climate to stimulate investment, and by having public-private partnerships so that we can work on the things that we need to work on outside of the fusion reaction to actually get us to a commercial power station.
And within that, what do you think are the key, the key rate limiting factors? What's going to put the brakes on us getting there?
Oh, goodness. Well, that's a good question. Well, I don't know if it's even a long list, but there are always things that we don't know about as well. But I think that materials is a big challenge, because the materials are going to affect the longevity of the machines, and therefore the costs of the machines. Because if you have to keep, and also the designs of the machines potentially, because if you have to, for example, magnets, if you've got high temperature superconducting magnets, or any superconducting magnets, they're at a really cold temperature, you need to stop them from heating up, otherwise they won't be superconducting anymore. So therefore you need shielding and insulation between the hot fusion plasma and the neutrons that are being produced, to keep them, to keep the magnets away and keep them cold. The more shielding or protection that you put in, the bigger the machine gets. The bigger the machine gets, the more the costs go up. So materials is a huge thing. And so you have a design consideration where you can say, well, we can use less shielding, like a smaller amount of shielding, and that will keep the costs down. But we might need to replace the magnets more frequently, and the magnets, as we heard earlier, are an important, expensive part of the machine, and that's going to put the costs up. So it's a real balancing act between these things. So if we had better materials that were better shielding, in smaller spaces, then you could do both those things. You could have the longevity and you could have the costs of the smaller size. So there's a lot that still needs to be figured out, like on this journey, if you like. And to go to the other question, like, this is why simulations and computing power is important as well, because if you can model some of that, that can be helpful too. So I think materials is going to be a big factor, because that's really going to come in, that's going to affect the cost of the machines and the longevity of the machines. So I think that's a big one.
Great, thank you. I'm very conscious of time and the need to draw this session to a close now. So firstly, from a personal point of view, thank you to Tony, to Matt, to Melanie and James, both for your time and for sharing your insights today. It's been hugely helpful and insightful to me, so thank you. I'd also like to thank the audience. Thank you for attending today. It's a shame that we couldn't all be here in person together. I think we're getting there, aren't we? But we're not quite there yet. So thank you for joining today. And with apologies, we couldn't touch on all the questions that were asked today. But there's a lot of very interesting questions coming through the chat. So hopefully we've been able to pick a section of those, or a selection of those that have been informative. And finally, and Matt did mention it, if anyone wants to download the reports, there's also a useful exec summary. Both documents are on the Institution of Mechanical Engineers website, and they're also on Assystem's website, www.assystem.com. And there are also links to both on both the IMechE and Assystem's social media channels as well. So without further ado, thank you for your time, and I hope you enjoy the report. Thank you.